The first 3 weeks of the eruption here in Hawaii, crazy things would happen in the middle of the night. A new fissure would open up and it would threaten a new neighborhood. Thousands of people were evacuated from their homes. I started the Hawaii Tracker Facebook group to help people understand what's going on and get their questions answered.
Hey, how's it going? We're live. This is Fissure 20.
We had hundreds of people all throughout the neighborhoods sending in videos, articles, and images. We spend a lot of time making sure the accurate information gets out.
This is live. There's still lava moving.
They weren't just sharing a story, they were helping their neighbor. If a family was being evacuated, my group would just jump in and help out. So it was huge. They were watching out for each other.
Hello everybody, thank you for coming. Thank you for the support from everybody.
As we go through this, we're growing closer together as a community. When tragedies like this strike, you really realize how much you need each other.
Hello everyone, I'm geologist Philip Ong. Here bringing you guys another Kīlauea volcano update. 2 months into this eruption that started on December 20th, 2020 and is now reached today, February 19th, 2021. We're going to give you guys a full 2-month rundown on pretty quick, but kind of take you through a little bit of all the USGS video clips, recapping how the eruption went on, how it began and progressed and how it changed, those kind of things. And then we're going to come back and look at the monitoring signals like the tilt and the GPS, any earthquakes and that kind of thing as well. And we will take a set of questions at the end, starting you guys off here with the most recent USGS video taken from a drone UAS on February 4th. So a couple weeks ago, but it kind of gives you a little bit different perspective of the lava lake. You can kind of see down here at the bottom left, there's our west vent filling the active lava, which is kind of in this crescent shape like this nowadays. And with this big island that's been floating around and kind of parked itself there in early mid-January, and this whole eastern half of the lava lake has been crusted over ever since about January 8th or so. We'll look at all that in a little bit of detail, but so start you guys off with a little bit of a peek at how it looks like right now before we jump back 2 months in time and look at the USGS video here. Let's do that here next. Mahalo Dane DuPont's with me, taking questions on the chat, manning the chats, checking our streams. So we will be trying to get you guys both ways here today. So all right, let me let me take myself off the screen here so you guys can see all of this presentation here. Let me play this video as I talk. So let's start off here at the very beginning. And this is a model USGS released of the water pond that was filling from July 2019 until it was vaporized in December. So here's a time lapse of that water lake filling. Kind of see it a little bit close in. And we'll zoom out a little bit here. We've kind of compiled various USGS time lapses to kind of make it a little bit more continuous. The wide view, the whole thing filled 51 meters, 167 feet in that a little bit over a year, July 2019 to December. And then the lava came out of the ground, and you can see it there. Thermal camera now, water lake, steam, lava, north vent here, putting lava into the crater, making an island. Views from Mauna Kea on a time lapse. You can see the lake glow, the steam cloud from the lake vaporizing. And here we actually get to some of the first closer in images released by the USGS. Fissures in Halemaʻumaʻu from the north and the west vents, filling that whole crater bottom almost 500 feet in 2 days, 140 meters. The island was already present at the very beginning from interaction with the water, but as the lake filled up, it essentially drowns that north vent and allows the west vent to become an easier path for the lava. And here you see the thermal north vent is active on the upper left. And it's going to switch over to the bottom where the west vent's located. Then the island is kind of drawn towards the vent, whether it be from currents underneath the surface or for some pressure gradient on the surface. It's not quite clear, but they do seem to do that, have that kind of effect. This is a nice USGS animation, the basalt berg islands. We discussed how to call them, drifting in that lava lake. You know, all pieces of cinder piles essentially that were formed from the initial fountaining events, the higher fountaining of the lava from the north vent, especially as it interacted with that ponded water that was in the ground there. So here's some aerial views: January 7th, January 12th, February 1st. Here's that aerial USGS drone fits in here, February 4th. And then there's one more, February 9th, that was released as an aerial as well. All right, we're going to focus on the north vent here a little bit. And you can kind of see there it is. That was initially the easiest path for the lava to come out. And it was pooling in the bottom of that crater. You see it bubbling, and you already had quite a lot of material. All that darker stuff is the island forming there. 2 billion gallons, 10 million cubic meters in those first few instances there, yeah. You can kind of see as the lava splashes in at the edge of the lava lake there, how it's really charging at the beginning, up to 50,000 tons per day of SO2 in the first few days, and correspondingly lava volume is really at the highest also. And after 5 days, almost 600 feet deep, and that's what essentially drowns that north vent, and that brings into the north vent on the 26th. That was really the last day we saw of it in December. So it's really been all about the west vent and how it's changed. You can kind of see this first aerial from December 21st. December 22nd, and a little bit less active. Those lower vents were quickly submerged. We're not sure what's going on down at the bottom underneath the lake surface anymore. But the upper vent we can kind of see has been active a little bit less. On Christmas Day, it was actually not active at all, but then it reactivates as the north vent submerges on the 26th. And then the next day, it really takes over Eruption as the only source of lava that's been filling the pond ever since. You can kind of see from that, remember how tall that cone looks back in late December, because as we progress, you can kind of see there's pressure cycles. It kind of crusts over, bubbles up, and makes a dome fountain. Then the cycles come forth again, and it repressurizes, it bursts out the cone crumbles. It all that lava splashing out of there is what's falling down and making that edifice, but it's also making the edges unstable, so they fall back in on themselves as it grows and falls apart all together, as you see right there. And that was kind of the last time we saw some really high pressure was, that mid-January time when we actually saw that second north fissure reactivate and put out a second source of lava over there on the upper right side. So this is sped up a lot, 500 times, but you can really see the pulsation, how it's really cyclic fluctuations in the vigor. And so by the end of January, we're into our low that we were still in today, where we have the whole west vent crested over. And so now we'll focus on that entry point where the lava is pouring into the lava lake. Kind of see, focusing in on that plunge point, right? That kind of entry into the lava lake. We start off with a little thermal here from December 29th. You kind of see the whole upper part of the vent closed off, and it's really about the plunge point. So as the lava is forced through a deeper underground pathway, it's bubbling up more and more and more, especially as it's getting ready to burst forward again with more gassy lava in a couple of days here in mid-January. You kind of see it goes through, slightly gassier, slightly more sluggish, and then here's where it's going to be starting to charge more, shooting out of that channel down the side of the cone, and then pulsing. In the same view, just kind of focus in here a little bit more on that actual exit point. And you guys who have been following our channel have seen this a couple of days ago, this little preview of this particular part where we see the plunge point here coming into the lava lake. Here's something new. Here's the upper west vent. I see it was really charging when eruption really began on the 22nd. By the 23rd, the north vent's more preferred, so it's kind of dying off. But by the 27th, it's back active again as the north vent's done by that point in time. It was really pretty quick. And then resurging on the 11th there. And, more recently, the second vent opening up on the right side there in the north. The video of the flames shooting up on the sides of the cone as lava bursts from the middle. And that's our most recent view. It looks like that. A couple last things here. The lava lake crustal foundering is something that's been happening kind of continuously at those edges of the lava where it's shallower or where, it's kind of crusted over. So this is really sped up. It's the whole crust being consumed by the lava overturning and replacing it with new crust. And this is a process that would happen over and over and over again, essentially until you run out of enough heat to break that crust and resurface the whole thing. The lake, as it rose up, made this perched rim, which it would breach, and that's still happening from time to time now. And so you can kind of see zoomed in a video example of that right there, where it really focused in on that little area. All right.
So we have a $20 super chat from Natasha. Says that it does appear that does this appear to be fresher lava? I remember the graph of probable old pools of magma from the prior eruptions. Is there a way to tell by the viscosity of the lava or only by the USGS testing the chemistry of the lava?
Yeah, great question. Thank you. The chemistry is really the best surefire way, right? We can kind of look for the signs of the gassiness of the lava, but that's something that's from where we sit in the public data. It's a fairly subjective thing, right? Maybe they have some better way to quantify it in-house that is more novel and being tested still, right? That's not quite public, but we're not privy to that, and so really the chemistry really is it. So I've been looking like the frothiness, how gassy it looks, as some indication of how hot it is usually, and how young it is as well, right? So how deep it's coming from, rather than being recycled, it drained back through the vent before, or something funny, it kind of took longer coming up through the throat of the volcano, so it kind of, maybe it's degassing while the main channel came to the middle. There's some slower stuff coming up the sides, possibly. There's all kinds of dynamics. We don't really know what's happening underground in there. So yeah, it's a great question. I'm looking at essentially these signs of, when we look at the west vent changing, how bubbly the lava is coming out, as the best indication of that, right? So it seems like, kind of recapping what we just saw, we had that initial big pulse. We had the switching of the vents. We had a real increase in vigor at the west vent after it kind of died off a little bit, and then after that second pulse came through, it's really been kind of waning ever since then. That's the big picture that we can see, and so we'll look at that in a little more detail as we go through the process here. We'll look at the thermal time lapse next, and here we're starting off with this orange. I'm kind of not showing a temperature scale here on the right. This is all USGS HVO imagery that we are compiling into these time-lapse animations. Yeah, and mahalo Bob Martin for your work with capturing all these images. All right, so this is going to go pretty fast. We're going to do the 2 months in about a minute here. So we'll start off with that lake of water. We're going to see the lava burst forth from the west vent over here, from the north vent over here, go into the water lake, create a giant cloud of steam that's going to obscure most of what you see here. And then you'll see the lava flowing in, filling the lake with an island that's kind of the remains of the lava meeting this pond of water that's here at the beginning. And so let's see what happens after that. We'll kind of talk our way through it. So all that happened pretty quick. Here's a north vent. You can see there's that big island, and north vent shuts off. West vent activates. The island comes here, it takes a turn. It kind of aligns itself long ways against the vent, and it seems like that stops the circulation a little bit. And perhaps, maybe it has effect, maybe not. But in any case, the back half of the east half of the lava lake crusts over, and lava is still going underneath there and lifting up through the cracks on the edges, all through there. And building a perched rim, like an above ground swimming pool, all through here. And spilling over those rims as well. Right, and starting and stopping, fluctuating, and having more chunks of cinder, whether they be from this particular west vent or the other west vents that were submerged underneath the lake way over here, or there were chunks of, there's all kinds of cinder floating all over the place. You can kind of see here we're approaching the end here, and the last few days has kind of just stayed bubbling, recirculating mostly within that crescent. And at the same time, you do see these squeeze-ups on the edges, right? So it seems like we're no longer flooding lava around the backside of this island. Instead, we're lifting this whole thing as a lid. Right? So it's interesting. I wonder, what role this island plays in that, because we saw that this island has been happily rising and falling with the tide. Right? What I can do now with this video is I can grab it and drag it backwards in time, and kind of, if I can do it really fast, you can see how the island, as it rotates and moves and rises as well, and even that whole crest at the back is rising as well. And so maybe that island becomes a float of some kind that helps that crust over there stay more buoyant, right? And USGS mentions that that crust must be frothy enough to be dense enough, or frothy enough to be light enough, that all the lava is denser than it when it's degassed and stays underneath it. That's fascinating. I'm trying to go a little faster here. I really see that change. So that's our thermal time lapse right there. Right now we have basically just these little base shallows where that foundering process is happening. Not as much over here on the west side today, but otherwise seems like fairly deep circulation all through here, but still leaking out the edges underneath that big piston head. Well, that is what the thermal looks like. And you can kind of see the most recent volcano watch issued by USGS today is exactly about that. It's it's an image they released back on February 1st over here. We'll zoom into a little bit more, but essentially it's describing all these things we're showing you guys on a thermal time lapse and have been showing you guys for 2 months now. And kind of zoomed in. It's great to have this in graphical format, so mahalo USGS. You can see they're pointing out the levees, the active lake surface, the inlet, the western fissure, the overflow occurring past the levee, the island, this eastern half solidified on a surface, and this warm ring of ooze-outs along the perimeter. And all these things that we've been discussing and showing you guys on the thermal as features we've learned about as eruption has progressed and they come into being. So February 16th, image here of the west vent. You can kind of see same lava still coming in. We haven't seen much on the face of the vent in a long time, so it's still coming in, but it seems to be maybe slowing down, right? The gas amounts are less also. In fact, the lava level is the same as it's been for all week, essentially. At least starting and ending, it's fluctuated up and down, as the change in slight inflation, slight deflation has put a little bit more lava, a little bit less lava out of the vent. But there's also a constant degassing, gas bubbling out of the lava. And as that happens, the lava kind of compresses itself, right? It takes up less space, and so the whole surface can settle downwards. So they're seeing that the lava was coming out slowly enough, even though it kept coming out slowly enough, that the crust level was actually dropping some of the days this week. So that, combined with the low gas values, and the lack of any other pulse on the front of the cone is interesting. And if the eruption does come to an end, these could be things that we can look back and say, well, maybe those would have been signs if we knew for sure, and we don't know for sure at this point in time. I'm just kind of discussing the patterns we see here. So that's the photograph of February 16th, USGS HVO. Let's jump to their photo and video chronology for the 18th. And so they go back to the UAS flight and they point out a couple of these photographs here. So kind of similar things as we've been showing you guys, and kind of just scroll through here. Different views. View of the backside of that island is a little interesting because it's something that a pattern we've seen in other places on the photograph as well. We have that lowest ledge where the lava level was before it dropped down a little bit and hasn't quite come back up. And we have an upper ledge where the lava was, when it was much gassier and frothier, it was lapping up on the edges all the way up in here. A little bit harder to see when I draw all over it, but that is what is happening there. All right, so a couple more. You can kind of see they've zoomed in here on some of the other little islands on that crusted over eastern part, and they're saying that the length of this island, I'm kind of take it to be from here to here, maybe like that, right, from there to there. Be about 50 meters, 164 feet in length. Give you some idea of the size of these things, right? So 50 meters, about 50 yards, so half football field, right? So you're talking about a football field, maybe something like that size on there, more or less. Give you guys some idea of the dimensions of that. Some upper rights over here. Get some idea. Size of these pieces of rock that we believe were interactions of the water and the lava when it was first coming into the lake on December 20th. Yeah, that whole lake vaporized within about an hour and a half, according to USGS. And so that was that really most violent, most steamy part of the eruption by far. So here's the plot of lava lake depth. You can kind of see that in green on the left is where they were measuring it manually over here when it came up pretty quickly in those very first few weeks. And ever since then, you kind of see that by around the time that we switched from the north vent to the west vent. Let me zoom in a little more. Right. And we switch over, and about around the 26th from the north vent to the west vent, we kind of have a new rate of increase. Right. So the depth is still increasing. At that point, it was about 180 meters. Right there. And at this point now, we are somewhere close to 220, not quite 217, more or less right in there. But if we zoom in on the right side of this graph, you can see that we've been pretty stable for the last week or so. Right? A little bit up and down. You have to ignore this. It's probably bouncing off the steam when the wind is blowing the steam in the path of the laser. Ignore those things, but you can kind of see there are times when lava level has gone down from the gas coming out and back up and back down, and now it's actually a net stable, right? So it's losing gas and coming in at about the same rate, it seems like, more or less. Okay. So what does that look like in map form? Here's the most recent map from February 11th. I can zoom in a little bit more and start kind of close in here, and we can kind of see in black the trace of the 2008 to 18 lava lake. It's about that size. And that's more or less the same size as that former lake of water got after this 2018 lava lake drained away to feed the 2018 Lower East Rift Zone eruption. And after about a year of the rocks cooling down, the water came in. You guys saw the time lapse. That's the area it took, about the same as that, right? And so that area of water is what the first lava came into, and that's about the same area as you see this more orangish island. That's all the cinder that formed from that original interaction of the water. It obviously came over and rotated, as we saw happen on a time lapse. Right? It probably came this way first, and then back this way, and then over here, and then over this way, and then rotated, to be honest. But something like that. Right, and as we've discussed for a long time, here's in green, an 800-meter elevation contour. It's what it would take to spill out of that innermost crater right over here on this northeast edge. It could come up a little bit lower than that, maybe to 760 or 780, somewhere in that range before it's visible from the overlooks, public overlooks over here in the national park. But as of yet, no confirmed sightings that I'm aware of but from public viewpoints. Obviously, the USGS is standing up here on the rim, where the public is not allowed to go. So that upper edge of the block over here on the right is 900 meters, and 1,000 meters way over here at the bottom is the elevation of that caldera wall down here on the south side. Right? And so from that point on, and if lava were to fill up that high, it could possibly go this way as well as out this direction over here into the main caldera floor. But that's the point where USGS is estimating years for that to happen. All right, so kind of zoomed out and kind of see the contours there. So we have some statistics as well. The surface ends up being 2,400 feet above sea level, 730 meters above sea level, and depth below the rim, 67 meters, 220 feet. The depth from the surface to the bottom of the crater, 216 meters, 700 feet, 709 feet. Active lake area now, that's this kind of just a reddish part, because it's kind of closed off to just this crescent-shaped red part. That area now is 19 acres, 8 hectares. And the total lake area, the whole pink thing, that's 104 acres now, 42 hectares. Total volume of 9 billion gallons, or 35 billion cubic meters. And that's the most recent information we have as far as those kind of figures. All right, and so one more view of that, you can kind of see, looking at the thermal version of that. Over here, the brighter colors, this is that crescent of newer lava. You can kind of see the reddish where it's the most, bring out the most heat there, the highest thermal signature. And you kind of see only a few cracks in between the crests in some places, and coming from that vent source right over there. So interesting, right? You don't see anything red in this shallow area right over here. A little bit kind of through there, but that gives you an idea of the circulation, and it must be going all the way into over here and over here. And of course, we do know it's going underneath the crust and popping up areas like over here where it's a little discolored. Okay, we're going to look at the monitoring signals now on the tilt. And so what I've done here is I've taken from Volcano Awareness Month, the USGS put out this, at the time was the last 2 months, that was a month ago of tilt, so it goes back to November. And we're going to add one more month here at the end on the right side of it. Right? And so we're looking just up to the blue line. The green line is meaningless the way, because I picked out the one that didn't actually match, but the blue line does match. So we'll look just at the blue line as Ue Kahuna. And you can kind of see here, back in November, we were having deflation inflation signals. I'll zoom in so you guys can see a little better. Having deflation inflation signals. And then we had December 2nd, this intrusion. That was our first real sign that the pressure was at a breaking point, where lava actually injected towards the surface. December 2nd, didn't reach the surface, but that was the intrusion we detected as a big deviation on a signal on the tilt. And it turned out that, well, not quite 3 weeks later, on December 20th, is when the eruption began. You can see here this big drop in the blue line is that signal of relief of pressure from the beginning of the eruption up until the drowning of the north vent right over here. Right, and so from that point on, after the north vent drowns, and kind of pressure builds back up for maybe a week or so, not quite a week. Then it starts relieving pressure again, going downwards. We start having deflation inflation signals again within the caldera, within the active eruption. Possibly some smaller variations as well. We had to, but generally a net rise until we have another deflation inflation back-to-back doublet here with a rain bump. And then scrolling back over here to this current month, looking at the blue, we had another double deflation inflation, and really for the last over a week now, we're in a steady, wiggling up and down a little bit, but really pretty steady, stable with no up or down. So the question now remains, are we going to keep having these pressure cycles, or are we going to just stay steady and wind down to a halt? And so only time will tell. But that's where we are right now. I'll zoom back out so you can see that these variations and even this climb we've had back up, right, coming back up, doesn't really match up to the total amount we dropped down. It's 45 microradians at the beginning of the eruption. So this is a match to scale and time here on the right. All right, so that's what the tilt looks like. So if we actually Go to December 2nd, we actually had a whole series of earthquakes that came through. USGS released on December 17th this volcano watch that discussed all these earthquakes. And it was something that at the time we weren't really sure how significant it would be, but they suggested the intrusion was small, anything from 10 to 30 times less magma than intrusion of May of 2015. And the equivalent of about 1 or 2 hours from Fissure 8 during 2010 eruption. So even though small, potential clue for future behavior. So that's what in the end we'll look back as the real major foreshock, so to speak, of the eruption. Because on the actual tilt plots, the tilt deviation begins only about 1 hour before the eruption, and it's not a huge drastic drop. We're essentially dropping 2 microradians in an hour, right? With Kahuna. And so that's 8:30 and 9:30. You can kind of see here, there's a little bit of a change in direction on the southern stations over there, but not a huge change in the tilt that was visible ahead of time. I'll zoom in a little bit, give you guys a little bit better view there. All right, we've discussed this in the past, just a little recap here. Not a huge sign in a tilt coming ahead of time. Looking at the past year, you see a lot of these deflation inflation events all through here in this upper tilt plot. And kind of from June, this more gradual climb from about a background of minus 20 microradians to plus 20 microradians. About a 40 microradian gain we got there over those not quite 6 months there, maybe about 6 months or so, right? Before it actually kind of slows down, and then we have the pop with the intrusion, and then the pop with the eruption coming down over here. That's the past year. On the top, it's the tilt. On the bottom is GPS. This is a vertical component of one of the stations, and you can kind of see a very similar pattern right there, right? Like going back to about June, you start to see the distance, the swelling, right? The ground is lifting up higher, and then it starts rising up higher, and then it actually jumps up for the intrusion. Still climbing, drops back down in relief as lava breaks the surface. And that was about back up to about a month ago, the GPS, right? So there we have it, kind of the big picture of the tilt and the GPS. As far as the deflation signal, I'll just recap this as well. At the beginning, it was all going inwards. All these arrows are pointing inwards. Zoom them in for you guys here. So the bottom of the arrow is where GPS station is located, and the size of the arrow, the length of the arrow, is the magnitude of change it experienced in the direction that it went in. Everything's contracting back towards the eruption source. It's kind of like popping a boil of some kind, right? Where that's relieved all the pressure and everything is sagging towards that point. And that's the story at the summit. And you can kind of see that since then. We'll just reload it and make sure nothing has happened in the last little while, and you can kind of see here's our last 2-day plot. We're at a scale of minus 0.3 to plus 0.7, so less than a microradian change. Zooming out to the last week, you kind of see it's pretty flat, really. In the last month, definitely still nothing's changed. Okay, so as for the rift zone, let's scroll down here. You can kind of see the GPS line in the past year. Well, let's finish the summit GPS, and then we'll go to the rift zone GPS. And so the summit GPS, we saw everything up to around here on that last plot. But since then, what I want to show you guys is zooming in here to the last 2 months of eruption. You see that after that initial drop down, we kind of follow the pressure cycles up and down, up and down, up and down, but with a general upward trend. And that upward trend means the caldera is spreading. It's getting wider still, and that usually indicates magma coming in. So that's the one signal that's at odds with our decreasing gas values, with our decreasing eruption values that are implied by USGS updates. So that's the kind of the paradox that we're in is, and it may be that, you know, the eruption ends while it's doing this, and then it just keeps inflating, and at some point it does one of these again, where it pops to the surface again. So that's kind of a pattern that's been seen before. Is as soon as eruption is over, so to speak, it can start re-inflating and repressurizing. But it's strange to see it repressurizing kind of before it's over and while it's trying to be over. So we'll see. This is still the biggest paradox of what's happening now. Okay, so okay, rift zone. Rift zone's down here. This is distance across Pu'u'okona. It's not loading the graph I need. Let's try it again. There it is. So this is across the rift zone by Pu'u'o. and our eruption begins over here in December on this time axis on the bottom. And so you can kind of see that it also, from June, was showing signs of spreading, right, until kind of was maybe full right around here by October or so. And that's when we start seeing adjustments happening at the summit, and kind of stable until the eruption happens at the summit. And then it's been contracting back down. It hasn't quite reached the level it was back over here. You can kind of see it's getting down there, right? So, you know, it's sagged almost back to where it was before this extra surge and magma made it into that pool area of the rift zone. And we don't see this anywhere past pool, and that's what this plot is that I keep trying to get to is really for. The same kind of thing where we're looking at the summit GPS here before. Now we're looking at all south flank stations. You know, there is some movement, but not nearly the magnitude that you see at the summit. And if you look closely over here, you know, east of pool, there's nothing. There's no movement anywhere over here. So the only place you have movement, it starts over here by Pu'o, and it's moving back towards the summit. And together across Makapui, kind of indicating that the magma bodies that live underground all through here are all feeding back towards the summit and deflating. And so that's been the signal of the rift zone. Nothing has changed there. But since we are doing a full synthesis recap, that is part of the story as well. Okay, so as far as the gas did not show any precursory signal. We thought maybe we saw a couple of spikes here and there, but it was really hard to tell, and largely it might have been because of the water scrubbing a lot of the gas from the magma and not allowing us to see it at the surface. So you can kind of see the eruption begins by this dashed line over here. This is from the Volcano Awareness Month as well. And you can kind of see the spike in gas at the beginning. It climbs upwards before trailing back down. And so that's just that first day or so. And we kind of zoom out and you can see that the highest values have an error close to 50,000 tons per day, down close to 30,000 tons per day at the bottom. But afterwards, after that initial pulse upwards, then the measured values came down pretty quick and have stayed down and actually been decreasing below this later in 2008-2018 lava lake era measurement of 5,000 tons per day. At its onset, the 2008-18 lava lake was up around as 15 to 20,000 tons. So we actually crashed right back through that, and below, we covered a little bit around this 5,000 tons, and then we've really been on a decline, and now we're down around 1,000 now. So it's really been a long, slow decline. Here's the plot that doesn't still have the newest measurements, but there's new measurements in the 16th. 1200 right over here as well. Same pattern that we've been showing you guys, so that kind of ties it all together, I hope. Okay, so there is definitely a fog still coming out of the volcano, and a fog is blowing down wind and affecting communities. Ocean View, Pahala areas, perhaps upper Pahala reaches, and wrapping back around to the Kona areas as well. And so that is still happening, and something that should not be forgotten. But there is also use in the gas, and so one result that's been coming out of the gas chemistry, from the first time they flew the drone, and we'll be interested to see what they report from the most recent drone flights that we know happened a couple weeks ago, is that they found low ratios of CO2 to SO2, characteristic of magma that has already degassed CO2 in a relatively shallow chamber. So it's been sitting around in the system long enough that it's lost its CO2 already in the past. So it did not rise quickly from deep in the mantle. But that was so far with the beginning of the eruption. So we're kind of still waiting for more information on that. It seems like, like maybe the pressure is relieved, and and we're still long-term building up. And I would expect, if this does end, have another eruption and not too far a distant future again. Okay, as far as earthquakes, I went back and pulled this out of one of our earlier updates. This is the 1 month of earthquakes between November 17th and December 17th, 2020. So this is 3 days before the eruption. Right, and so we have similar patterns. The Pahala earthquakes have always been going on as far as we've been showing you guys. But kind of zooming in here, you can see quite a lot of action in the summit region. I'm going to change my color here. See this whole summit caldera is right in here. We actually have an arm in the upper southwest rift zone, an arm in the upper southeast rift zone, all the way down, and actually around the corner all the way to Pu'o'o right around here, showing signs of seismicity, right? So that's how pressurized the whole system was, and that's why we consider this to be more or less the biggest possible extent of that shallow magma connected chamber, so to speak, right? If it's a chamber or a pathway or network, what have you, it might go all the way to pool 1, so that's what we see contracting, right? Something like that. But really, it's all coming out of right in there as the weakest point.
We have a $6.99 super chat from AH Boomer. Love the video on the geology history lesson on the hotspot. Learned a lot and love to see more of those. Very educational. All right. Thank you, sir.
Mahalo, mahalo. All right, so this is the earthquakes that was a month before the eruption, and now I'm going to switch it to this previous month from now. You guys can see a much different pattern now. So we still have earthquakes on the south flank over here, right? Kind of south of the rift zone, whose trace is around like that. So there's still a few earthquakes in the rift zone right in there, but not anything like before. Right, everything is south of there. There's nothing at all in this upper south rift zone, and you actually can see the caldera underneath there for once, which you couldn't before. So that's a contrast between before the eruption. So certainly, this is something we were talking about for a while. There were earthquakes were definitely elevated, and in fact, that's why we kind of began stepping up broadcasting at that point in time and updating because of this exact pattern in here. So if we look at the right, scroll no. Look at the earthquake counts. Here they are. This is for the whole last year. So going back to March 2020 in the left part of the graph there, and on the left here is earthquakes per week. The top of the graph is 900, not quite 1,000 earthquakes per week. And this is Kīlauea. So you can kind of see that we have some variations up and down on what might be a background of somewhere in there, right? You remember we saw our GPS signal starting around June, July, and you can kind of see that we start having bigger earthquakes. That's what this red line jump means, is the energy released, total energy release. We had a bigger earthquake usually when you see one of those. So bigger earthquake, and then we start seeing seismicity build up from September to November, dies back down, and then actually picks back up in the beginning of December. It's back down, picks up a little bit before the eruption begins, and then since the eruption begins, it's been down at very, very low levels, and that's kind of the story of the earthquakes. So here's an earthquakes map on the island, and what I've done today is I've actually put on these white dots for the whole last month, so you can kind of see the overall pattern, right? So Pahala earthquakes are still something that happens in the background. We've talked about those, and there's those south flank earthquakes, and not a lot in the rift zone over the last month, right? This has got a different threshold than that automatic USGS map, which picks up smaller earthquakes. So this is, kind of gives you a better idea of the ones that we're counting, and not a whole lot of action there. And we'll pan over to Maunaloa, which is how we'll end today before we take our questions. And you see there has been activity in the last month, kind of at the summit and these typical regions around the summit and upper southwest rift and a little bit northwest of the caldera. And you kind of see, let me scroll up here. For the past year, those are the active areas. The volcano is still building up, but there hasn't really been a whole lot of change affected by the Kīlauea eruption, which is our focus today. So looking at the earthquake rates for the last year, you can kind of see that there was it's got a background with up and downs as well, a lot of up and downs, right? But it kind of ramped up here in August and came back down, came back up in October, down in November, and up in December, and then down, and now it's climbing up again. And it, even at this level here on the right, 200 earthquakes per week is not anywhere near enough to be worried about some kind of eruption, right? This number needs to be up in the thousands, at least, per week, if not thousands per day, right? For us to be really talking about an eruption seriously. But that's why we look at these, and you can kind of see that, even though we might be having a peak, it's not that big a peak over here, and there doesn't seem to be any real solid correlation with the summit eruption of Kīlauea. Although maybe in the details you might see some little variations, and maybe we can pick it a little bit further apart someday, what happens in Maunaloa. So we'll kind of close off with this. This is the most recent 24-hour time-lapse of Maunaloa. Still some snow up there, and you can kind of see all is quiet and calm in Maunaloa up there, and cold. All right, so with that, we will turn to questions, Dane.
Yeah, good recap there. Before we get into questions, I do got to thank whitetracker.com. Whitetracker is a community-based social media platform trying to build a more community-driven, uplifting social media experience instead of rolling flame wars. Best way to be able to help us out is to go to share this video. We don't have a budget to do publicity, so you sharing this video, like, subscribe, commenting, all that kind of stuff helps tremendously. Second way is go on hawaiitracker.com, become a member there, become part of the community. Third way is through monetary support. We do take donations through Super Chat and on hawaiitracker.com/support. And we do have some supporters that came through on there. Do want to shout out them, appreciate them. Charlie S. and Michelle B. Michelle B with the monthly donation. That's a reoccurring donation, keeps us going. Really appreciate that. So yeah, let's dive into some questions. So there was like a theme on the questions today. A lot of questions on the YouTube kind of went back to the dynamics of the lava lake draining and that impacting the shallow magma system and that impact upon the lower east rift zone, right? So I'm kind of aggregating some different questions on this one, but Brian and Randy and a few others asked about knowing that the crater floor is compromised by previous eruptions and collapse. How concerned are you about the entire lava lake collapsing under its own wake, and how does the lava weight on the vent work?
So I do think that the whole crater floor that the lava is filling has been pretty packed down from all the collapses in 2018, right? There are over 60,000 earthquakes, more depending on how you count them and catalog them and what kind of thresholds you use. And obviously you're not counting those all by hand, so you're trying to train a computer to pick them out for you, and you might be able to train it slightly better and get over 100,000 earthquakes, right? We'll have more news on that when those researchers are ready to share. But yeah, it's pretty packed down in there. Like it's kind of, it's like taking a jar of nuts and you just shake it, and all the loose rocks, all the loose ones the big ones come to the top, and the small ones go to the bottom, and they kind of fall through the cracks and accumulate at the bottom and fill in all those little gaps. So that's how we imagine that the whole structure of the caldera is. Like there's a lot of rubble filling the space in between all these big blocks that are all these big chunks, right? And then it's the chunks between the big blocks, they're the deepest ones that connect, whereas the rubble is kind of, when you look at a cross section, it'll be a little bit more shallow, kind of draping over and covering those features and obscuring them, right? So it's pretty packed down in there. So I don't think the actual weight of the lava itself is really going to change anything. It could, for example, change the slope of the angle of all that rubble on one side, and it could cause some little landslides to happen, or a big chunk, a chunk of the crater wall to fall in. That kind of thing is something that hasn't happened. But especially if the eruption were to slow down and were to see more inflation, then you might see the ground tilting underneath the lava lake, and then you might see changes from pressure beneath the ground. And that's where the changes really are. You can have much bigger change from pressure beneath the ground than from above the ground, just because you have a free surface where you actually can move things out of the way from below, right? You can actually push them upwards. It's a lot easier because there's space. You can displace air a lot easier than you can push down and displace rock. So that's fundamentally it. As far as the vent itself, the vent is probably a combination of lots of chunks of lava spatter that are all kind of amalgamated, all kind of glooped together, right? So it's probably not the strongest thing. It depends then on whether you can coat it in layers of lava, and if so, how many layers do you coat it in? If you plaster it enough times, maybe you can have a structure that might withstand, these bigger forces of magma movement pushing side to side. Or, if you don't, then maybe you actually it can knock them over or destroy them or erode them, right? That's the same dynamics that are probably happening at the bottom part of that island and all the islands. We don't know how many layers they have, what shape they are, or how much they've been plastered. If some sides are more plastered than others, and some sides are wearing away and other ones are not, and that's, who knows? But yeah, great question. Generally speaking, it's the underground adjustments that are going to change the shape of the ground and cause collapses. Collapses would happen probably if the magma underground were to move into, if it were to move in the rift zone, for example, Or there's a southwest rift zone, which is something that hasn't happened in a while, but the magma is really close to there. It's as close to there as it is to the upper east rift zone. And as we showed you guys in the seismicity before the eruption, it was connected over there as well. So it could go that way, and fill some little puka, some little hole, crack or something, and relieve pressure that way. And then that could cause a little collapse. But that's usually when collapses happen, is when you have magma leaving to go somewhere else, right? We don't see any signs of that. We don't see any signs of magma going to the rift zone. If anything, it seems to be coming back. And when I showed you guys a GPS plot of Pu'o'o, that trend is still down. It's still, it hasn't flattened out at all. So it's still contracting. It's still settling, collapsing. And if we were to look at the tilt, we'd see the same kind of thing. There was another slip event that seems to be happening. Pu'o'o. So the ground is still very much settling and adjusting all through there. And you'd expect a reversal in trend if magma was going back in there, right? So that's really the paradox, is why the GPS signal at the summit is so is increasing. And the real X factor there is the whole south flank, the whole south side of the caldera being attached to the whole south flank, moving south, and that could be pulling it apart, kind of thing, right? And so you'd imagine if you do that and you create space underground, you're going to induce magma to come and fill that space. And you can maybe sustain an eruption from that kind of, I don't know, that's where we're in the X factor, and, all bets are off.
So Joey Smallwood asks, this is probably, it's not a complex question, but I think it's a good one to just showcase. What's up with the spike in the electronic tilt at Maunaloa on 213?
Yeah, I'm gonna have to go.
So maybe pull back up that monitoring page.
I have to go find it here. Yeah.
Right, it's one of those questions that we get every once in a while, but we haven't covered recently, and
all right,
to people that haven't seen it before, it does look jarring.
Yeah, it's let's see what this one looks like. Right, there's kind of a couple. It's interesting here if we kind of look at this green line. I don't know exactly what's going on here, right? But we can kind of talk through what we see here. We can kind of see that there's an interesting kind of sign signal in here before and after, right? It's kind of continuing, so I'm not sure if there's what it's picking up, but there's actually an offset between here and here, right? So this could be possibly an earthquake that shook the ground and caused it to settle down at a place that's slightly different. Sometimes you see some weird kind of and then like a reset signal, like an electronic reset signal, and then it kind of goes. And then you might say, okay, someone actually went over there and rebooted the machine. I don't see anything convincing of that at this point right here. This looks more like an earthquake with an offset on the component, right? And then possibly a smaller earthquake jarring it over here as well. As far as overall magnitude, right, this is up to around 3 microradians from 0, so about 3 microradians. And that's you could get a lot more for the jarring of the tilt meter from an earthquake.
Yeah. Yep, thank you for that one. Yeah, the tilt meters are so many different weird little nuances to it. What was the rules of tilt meters? The first rule of tilt meters is don't use a tilt meter.
I bet the modern tilt wizards, we'll call them, would argue with those old timers nowadays that we've come a long way. But the old timers might have a point still, that you have to be careful for sure using that information.
All right. So Nicholas asks, is there so if it's degassing, the lava's degassing, then is the density of the lava changing?
Yep, exactly. Yeah, it is. It is the density of the whole lava body, the lava lake as a whole, is got to be changing for sure. Yeah, it's fascinating, really, right? Because and that's why a lot of times when scientists will discuss eruptions across volcanoes, they have to discuss the dense rock equivalent rate, right? You basically have to calculate, okay, what's the gassiness of it? Let's subtract gassiness. Now we can get a real volume of how much lava actually came out. Because otherwise, you can be really gassy and you can really miscalculate. You can't compare really frothy lava to really degassed lava. In the same way, you have to kind of calculate the degassed versions of them and then say, yeah, and by the way, this one also has got more gas in it.
So this is a question that we've had before, and sure we'll have again. It's kind of an interesting one, but in the long term, Jeremy asks, if this eruption were to go on for decades, do we have any idea which direction the lava would flow after the caldera overflows?
Yeah, I mean, it would have a long, long time to go, and it be spectacular to look at, to watch from the caldera rim, for many, many years, and then eventually it would spill out to the south and through the national park and the Kau Desert, away from many people. Yeah. So I mean, it's much more dangerous moving underground through the rift zones than it is spilling out of the ground from above, from where it is now. Yeah, so that's kind of the big question mark is, how does as always, it's always been a question from time to time on a volcano, like who's driving the car? Is it the magma pushing, or is it the south flank pulling? And sometimes it's a little bit of one, a little bit of the other. Sometimes they take in turns, and we're never really sure when they switch off. Right, so we're not sure exactly there. South flank's doing more pulling, or magma is doing more pushing.
Right. So this is also a question that we do get, but it's an interesting one. Trish asks, has anyone studied the possible connection with energy increases from solar event and geomagnetic storms in association with the volcanoes?
Energy increases?
I'm assuming that's like solar events, solar radiation, that kind of flux on the magnetic field.
I'm not sure that it's been measured on volcanoes per se. We do know that the lava itself has a very strong magnetic field of its own, especially when it's moving. So it might be too strong locally to be affected by the magnitude of the force from the sun. Even though there is a force from the sun, the magnitude is a different scale than the magma, the lava swirling in a lava lake. So there have been some studies done on tides, right? And if you have a very open system, you could have some tidal effects for sure, and that's something we'll have to revisit in the future. But that's the short answer on that. Yeah.
Right.
Yeah. So maybe let's take one more question, and then we'll wrap it up.
So, almost really does it for most of the questions that we have here.
All right. So.
Yeah, let's just go there. So one thing we are going to do that is a little different today is we are going to be premiering a video on YouTube immediately following this live stream. I went down to the Poʻiki Beach. The Poʻiki Beach formed following the 2018 eruption as sediment, rock, and sand washed in from the predominant currents of the ocean. From the north to the south, dragging in a bunch of sand and blocking access to the Poʻiki boat ramp, but also creating a bunch of warm ponds that were now sealed off, where previously they just pumped water into the ocean, so you hardly knew where these ones were. But now the hot ponds have gotten hotter since July, and this is a follow-up survey of the temperatures and the sand movement.
Yeah, check it out, you guys. Dane did a great job.
Definitely.
Anything else, Dane, before we switch over and run the Poʻiki video?
That does it for me.
Oh, mahalo, you guys. Mahalo, Hawaii Tracker. Check out hawaiitracker.com and sign up over there to get our updates. And we will be back with you guys next week, perhaps on Tuesday. We haven't quite finalized it yet. We may switch to a Tuesday-Friday schedule next week and try to keep our same 5 p.m. Hawaiian time target start day time. Although we do often sometimes have technical issues where there's just the two of us producing everything. So occasionally we do hit a snag and end up falling behind.
It happens.
Part of the process there. So, but yeah, so we'll be back with you guys on Tuesday. You can kind of check our channel. We'll post an announcement on there as a comment, when we'll go live next, and take questions and review the eruption at that point in time. So
and come check out the video. I will be in the chat on that one while it premieres, so we can talk about the changes down there or whatever you want to talk about.
Yeah, and this is on YouTube, right, Dane?
Yes, we're doing a premiere on YouTube. We will post a link onto the Facebook as well.
All right, mahalo, Dane.
It looks like we have one final donation coming in at the very end. Craig L. Mahalo, buddy.
Mahalo.
All right.
Well, thank you guys. Thanks for the questions. Hope you guys enjoy the 2-month recap. It's been fascinating. We'll see how long it lasts and what other treats we get to indulge in here with this kind of volcano science. But until then, until next week, for Dane DuPont, I'm Philip Ong. Aloha.